two ways we can graph this. We can figure out what the parent function does and then figure out what transformations are going on. In other words, there's nothing unique about the sinusoid function. It is a transformation is all it is. It's just like transformations of polynomials. So the parent function is y equals sine theta.
Okay.
And I know how to graph that. There's one period of it. Goes from 1 to -1 on the range, and the first period goes from 0 to 2 pi. Okay?
Okay.
So that's this function.
Mm-hmm.
Our function has two things going on, and you can do them in either order. The leading to is what? What is that?
Is that the amplitude?
Yeah, it's a vertical stretch factor. So if I wanted to plot y equal 2 sine of theta, it would just go up to 2, it would come back down through the same zeros, it would go all the way down to -2, and it would be like that. So the red is y equals 2 sine of theta.
Okay.
Now, what's the consequence of this 2?
Doesn't it change the period?
It does, but that's also a horizontal stretch or compression. When you change the period, that's what you're doing, is you're horizontally stretching it or compressing it. Now, that 2 is b, right?
Yeah.
What's the period equal to in terms of b?
2 pi over b.
Well, since b is 2, the period is pi, which compresses this thing. Instead of the function going from 0 to 2 pi, it now has to go from 0 to pi. And it has to have, in other words, it's going to compress. It's going to, if I quarter it up, these are going to be its key points right there. I gotta go up and hit my 2 there. I got to come back down through the x-axis at my second quarter point. My third quarter point, I'm going to be down here at -2. And my fourth quarter point, I come up to the end. Now all I do is draw a sine curve that goes through those x's.
Okay.
And you can see that the green is as if somebody pushed on the red, squeezed it together.
Yeah, I see.
So it's a horizontal compression.
Okay.
And notice that these go opposite one another. If the leading coefficient A is a number greater than 1, it's a vertical stretch. If it's a number between 0 and 1, it's a vertical shrink.
Mm-hmm.
If the number in front of x or theta is greater than 1, it's not a horizontal stretch, it's a horizontal shrink. And if this number is between 0 and 1, it's a horizontal stretch.
Okay, yeah.
So, like I said, there's nothing magical about the sinusoid function. It follows the exact same rules as all transformations do. In other words, if I put a minus sign in front of it, it's reflected over the x-axis. If I add 3 to it, that's a vertical shift up by 3 units.
Okay.
If I put something, if I say y equals the sine of theta minus pi over 2, that's a horizontal shift. Just like if I said y equals x minus 2 squared, that would be a horizontal shift of a parabola, right?
Yeah, okay.
And it's a
Okay.
horizontal shift because it's inside the parentheses. Well,
Okay.
same thing. That's a horizontal shift to the right by pi over 2.
Okay.
Okay? So no matter what function you give me, a sinusoid function, I can do it in the, I'm not quite sure why Trig does this, but they don't treat sinusoid functions like they're just polynomials. And they should, because you've learned for 2 years about transformations of polynomials.
Mm.
Sinusoid function is just that. There's 6 different things you can do to it. You can reflect it over either axis. You can vertically stretch it. You can horizontally stretch it. You can vertically shift it, or you can horizontally shift it. That's the only 6 things you can do to a sinusoid function.
Yeah, okay.
And
Okay.
all of those are the same 6 transformations that you could do to an algebraic expression.
Uh-huh. Okay, cool.
To me, the easiest way to learn sinusoid functions would be to treat them as a parent function that is being transformed. In other words, there's our parent function. Sometimes the parent function might be cosine, sometimes it might be tangent. But if you draw the parent function and then start looking at each adjustment or transformation, then you end up
Mm-hmm.
with the green line. And the only rule about priority of order is you do all your reflections first.
Okay.
Everything else does not matter. Since I did not have any reflections here, I could do that 2 first, or I could have done that 2 first. It would not have mattered. But
Mm.
if I
Okay.
put a minus sine of theta plus 3, since that's a vertical shift and that is a vertical reflection, I'm not going to get the same graph if I do them in different orders.
Mm-hmm.
You know, I mean, think about it. If I shift the sine curve first, it goes up to there. And now if I reflect that whole thing, it looks kind of like that. But if I reflect it first, if I reflect the sine curve first, that's the first adjustment. Now if I shift that whole thing up 3 units, notice it's in a different spot entirely.
Yeah.
So you have to do your reflections first. Whether the reflection is about the x-axis or the y-axis doesn't matter. Just do all your reflections first. And if you have 2 reflections, it doesn't matter what order you do them in. Just as long as you do your reflections before you do anything else.
Okay.
Okay? So I won't erase the sine curve yet because I don't know what your next problem is going to be. We may need that.
The next one's going to be a cosine.
Okay.
So the next one is y equals cosine 2 theta minus 4 pi over 3.
And like this.
The 2 is included in the parentheses.
Okay. That also matters. In other words, it matters whether the 2 is inside or outside the parentheses. And it makes a big difference, actually.
Mm.
Here's the reason. And maybe this has to do with why they teach it differently. This normally would be the phase shift, but in this case it's not. This C value is not the phase shift if there's a number in front of theta inside the parentheses.
Okay.
It only, in other words, B is still 2, whether it's inside or outside the parentheses. But the phase shift is different. Okay, if I want to know the phase shift, I got to factor that 2 out. Put it outside the parentheses, leaving theta minus 4 pi over 6. Notice that that's the same expression.
Okay.
Okay, the fact that 2 is now outside the parentheses doesn't affect the period. In other words, B is still 2. But what does change is the phase shift. The true phase shift is 2 pi over 3, or 4 pi over 6. But
Okay.
whenever they give you B inside the parentheses, then C is not the phase shift. The phase shift becomes C over B. If B is outside the parentheses, then the phase shift is C.
Okay.
So you have to be very careful depending on how they give you the problem. Believe it or not, the schools teach 3 different general formats. They are y equals a sine of b outside the parentheses times x minus c plus d. That's the most common one, and that's the one I like the most, because that's the amplitude. That you can figure the period out. That is the phase shift, and that's the vertical shift. The other
Okay.
format that they actually teach it in Colorado Springs, they don't use the upper one. They use this one, where the B is next to the X inside the parentheses.
That's actually the one that we're taught at our school too.
Okay, well, in this case here, A is the same, B means the same, but your phase shift is C divided by B. Because to convert the second one to the first one, I got to factor that B out. And so I end up, if I take the second curve, I end up with A sine of B times X minus C divided by B, because I factored it out.
Okay.
Okay? Both of them are just as valid. There's nothing better about one than the other. What matters is how they give you the problem. In other words, they could have given you the problem like this instead of like this. Those are exactly the same. It's just the top one is in the second format, the bottom one is in the first format.
Okay.
And the thing that's different is the phase shift. That's the only difference. In other words, in the top format, the phase shift is C. In the bottom format, the phase shift is C divided by B.
Okay.
Okay. And we can do either one. I'm always more comfortable working with this where you factor the B out. It doesn't make a lot of difference. The only real difference is the phase shift. So since I've got to divide C by B to come up with the phase shift anyway, might as well do it this way.
Okay.
Okay, now let's graph it. Let me erase my general formats here so I have a little room. In black, I will graph the cosine function, parent function. Also goes from 1 to -1 and goes to 2 pi. That is y equals cosine of x. Okay, I'm dealing in this one. So there's only 2 things going on here. There's a phase shift, and there is a horizontal shrink.
Okay.
Now, 2 is B, and the period, let's do the horizontal shrink No, you know what? Let's do it the right way. Let's do the phase shift first. But before I do the phase shift, what's the period going to be?
The period's going to be pi, right?
Yes. Okay. Now, the secret on phase shifts is to do the phase shift as the very first thing you do.
Okay.
And the phase shift is 2 pi over 3, same as 4 pi over 6. And it's right, then my first action is to go to the right by 2 pi over 3. Well, let's see. That's about there. Because this is pi over 2. So 2 pi over 3, I'm just guessing it's there. Okay? It's not vital that I put it in exactly the right spot for our purposes here. This is where I'm going to start the function. Okay?
Okay.
Where am I going to end the function?
2 pi over 3, you'll end at 8 pi over 3?
Well, remember what the period is.
Oh, the period's only pi, so you'd end at 6 pi over 3. No.
5 pi over 3.
5 pi over 3.
Yeah, which is about 5 pi over 3 is almost 3 pi over 2, so I think it's right there.
Okay.
And you can see that that's its period. From 2 pi over 3 to 5 pi over 3 is a period of pi.
Uh-huh.
Okay? So now that I have my beginning and my ending point, I quarter this up and put all my other points in there. In other words, what is this point, right? God, I hate this program. What's this point? In other words, I got to quarter it up.
2 pi over 3 and 5 pi over 3.
How do you find the halfway point between those 2 points?
Don't you just find the difference in between them? Wouldn't it be...
Add them together and divide by 2. Yes, that's how you find the midway point. So that's 7 pi over 6. Adding 2 pi over 3 to 5 pi over 3 gives you 7 pi over 3. Divide by 2, you get 7 pi over 6. Okay? And sometimes it's easier to quarter these up if you leave them unsimplified. In other words, remember what this started out was 4 pi over 6? And this we had 5 pi over 3, which is 10 pi over 6. Now it makes quartering them up a little easier. I would have come up with 7 pi over 6 a little easier, right? Just halfway between 4 and 10. Well, now I still got to finish quartering it. So what's that point right there?
7 pi over 3. 11 pi
over 6 now. In other words, we're finding the halfway point between 4 pi over 6 and 7 pi over 6. Add them together. Divide.
So you get 11 pi over 6. So 11 pi over 12.
You get 11 pi over 12.
Okay.
Okay. We find this quarter point, do the same thing. Add them together, you get 17 pi over 12.
Okay.
So there's our 5 quarter points, and we know that we start here, we come down through the x-axis at the first quarter point, we come down and hit our minimum value at the second quarter point, come back through the x-axis at the third quarter point, and we finish right there. We begin right there. So I'm going to draw the cosine curve through those x's.
Okay. Okay.
In other words, by starting with the phase shift and figuring out what the period is, I can figure out where to start my curve and where to end it and quarter it up.
Mm-hmm.
And I just draw a cosine curve through all the appropriate points.
Yeah, okay. Cool. Okay. So the next one gets into secant.
Okay.
So it's y equals secant theta divided by 2.
Which is the same as that.
Okay.
Okay. So the only thing happening to it, well, let's draw the secant curve. Secant's reciprocal of cosine, so it sits on top and bottoms of the cosine curve. In other words, the cosine curve, if I put that in there, looks like that, right?
Yeah.
So I drew one period of the secant.
Okay.
Okay. Now, the only difference between the curve we drew, this is a period of 2 pi.
Okay.
Okay, hold on. I keep trying to write and it keeps erasing. That goes from minus pi over 2 to 3 pi over 2.
Mm-hmm.
Notice the period of the secant is still 2 pi. And this is -1, and that's +1. With
Yeah. Yeah.
Okay, what is B here?
B becomes 4 pi.
Well, the period becomes 4 pi. The
B is 1/2.
period is 2 pi divided by B, so the period becomes 4 pi.
Mm-hmm.
And what that means is I'm horizontally stretching it.
Yeah.
But I'm not moving the whole curve to the right. I'm horizontally stretching it, which is like this.
Yeah.
And it's going to go from minus pi to 3 pi.
Mm-hmm.
And the important thing to know is that there's always vertical asymptotes right there. My original of the parent function, I would have had a vertical asymptote right there. Well, those vertical asymptotes get stretched. In other words, instead of the black vertical asymptotes, my asymptotes are now red, and they're going to be separated by 2 pi, each asymptote is. So I've got one there, I've got one here, and since they're separated by 2 pi, that must be at pi. And then I go out to 3 pi, and I got another one. I didn't leave myself quite enough room here, but I think you get the idea.
Yeah.
In other words, it's 2 pi between that point and that point, even though it doesn't look like it.
Yeah, I get what you're saying.
According to my label, everything is quadratic. My drawing doesn't really reflect the grid that I put on here. But the effect is the same. In other words,
Yeah.
start from if it's symmetrical about the y-axis to begin with, and you're stretching it, you stretch to the left and to the right equally.
Mm. Okay.
It is not. If we're talking about cosecant, which looks like this,
Which we're actually going to be at the next problem.
Okay, let's do it.
So the next problem is y equals cosecant, parentheses theta plus pi over 3, parentheses minus 1.
Okay. When you have a vertical shift, I prefer to do that first.
Okay.
Because my line of symmetry on all my sinusoid functions is the x-axis, right? My horizontal line of symmetry.
Yeah.
But if I have a vertical shift, that line of symmetry moves up or down by that amount. So I'm going to put a dotted line in here to represent my new line of symmetry. And this is what I would draw. That's at minus 1. Okay. So normally cosecant is going to look like, let me do it without the shift. That's what cosecant would normally look like, where that's 1 and that's minus 1. But if I'm moving everything down by 1, then my new cosecant, if I'm just talking a vertical shift, it's going to look like this. It's going to go down to 0. And this one is going to start at -2.
Okay.
Notice how they are both equidistant from my new horizontal line of symmetry.
Yeah.
In fact, if I wanted to draw the sine curve in there, it would look like that. So I'm sitting on the tops and the bottoms of the sine curve. Let me erase the sine curve so it doesn't confuse us. Okay, so this would be just the vertical shifted one. And it would go out to 2 pi. Okay?
Okay.
So now, instead of, the only other thing I have to do is the phase shift, right?
Yeah.
In green, where do I begin my curve, my cosecant curve? Right now, it's beginning at x equals 0.
You would begin it at negative pi over 3.
Good. Call that negative pi over 3. Where's the end of it? What's its period?
Its period is still 2 pi.
So add 2 pi to negative pi over 3.
So that'd be 6 pi over 3. That did end at 5 pi over 3?
Right, 5 pi over 3. Now let's quarter it up. What's that point? And you know what? I should really quarter it up on my line of symmetry axis, not the x-axis. So I'm going to quarter it up down here. Here's my starting spot. Here's my ending spot. I'll put x's there.
Yeah.
Where is this spot right here?
2 pi over 3?
Yeah. Where's this spot?
2 pi over 3 plus 5 pi over 3 equals 7. 7 pi over... Oh, whoops, sorry, I did the other
To split this one up, add this to this and divide it.
Yeah. That one is pi over 6.
Yeah. Which goes right about there. And finally, this point right there.
7 pi over 6.
Right. Once you get the hang of quartering it up, it's not that hard to do. Okay. So now what I want to do is draw the red curve only between these starting points.
Uh-huh.
Okay, well, this is my starting point. So the green curve's got to do this. Got to go up to there. No, it goes all the way to the midpoint. Excuse me. Hold on. Let me erase that. Starts here. Let's put some asymptotes on here. I got an asymptote every pi. So I got to draw my cosecant curve relative to these asymptotes. And I know that it goes down to y equals 0, right?
Mm-hmm.
So first one looks like that. And the next one goes up to -2 and back down. So the green, let me erase the red, because the red was strictly a vertical shift. But the green is our curve. The green is not only shifted down by 1, which means this point is 0 and this point's -2 instead of going from 1 and -1. And it's been phase shifted to the left by pi over 3. In other words, it's exactly the same as the red, only everything, and this is a horizontal shift. There's no change in shape. Because all I did was I took the entire red curve and I moved it left by pi over 3.
Okay.
And I got the red curve by taking the black curve and moving it down by 1. So really, I take my original black curve and I move it down by 1 and left by pi over 3, and that's how I get the green curve. But the order you do these in, I think it doesn't really matter. You can do these, there's no reflection, so you can do them in any order you want. But I have always found that doing the vertical shift first is a good place to start, because it allows you to draw your new horizontal line of symmetry.
Yeah.
The original horizontal line of symmetry is the x-axis, but when you have a vertical shift, it moves. And once you draw the new line of symmetry, then you can find your beginning point, your ending point, quarter it up, and put your graph on there.
Okay. Cool.
What else?
The next one gets into tangent.
Okay.
Sorry, I'm just finishing up this graph for cosecant.
Okay. You need me to back up my page?
No, I just finished it. Okay, so the next one is y equals tangent theta over 3.
Which is the same as tangent of 1/3 theta. The only reason I write it like that is because that makes b 1/3. Okay.
Okay, yeah.
Well, let's draw the tangent. Tangent also has asymptotes. What's the period of the tangent? It's only pi. It's not 2 pi.
Okay.
Regular tangent has a period of pi. And it goes like this. Always increasing, and it's asymptotic to both asymptotes. Then I have another asymptote over here that's at 3 pi over 2. I'll go ahead and put a second period in there just so you see. Something like that, okay?
Okay.
What's the difference between the regular tangent and our tangent?
it is spread out a little bit more? The
Right.
period
This
difference?
acts as a horizontal stretch because it's a number
Mm-hmm.
between 0 and 1. If that was a 2 instead of a 1/3, then it would be a horizontal shrink, and I would be compressing this thing.
Mm,
Okay? But I'm going to stretch it by a factor of 3. What's my period going to be?
3 pi?
Yeah. Instead of pi, it's 3 pi. And what that does to my curve is I have to stretch it in both directions from the y-axis. I can't just stretch it to the right. So the
Okay.
way I really stretch it is I draw in red my new asymptotes. Well, since my total period is 3 pi, I've got to go from minus 3 pi over 2 to plus 3 pi over 2.
Okay.
And I'm going to draw my new asymptotes. And I'm only going to draw one function in there. And it goes through 0 at 0 still.
Okay.
Okay, let me see what I can erase here. I don't need those vertical. The vertical asymptotes are actually pretty important. That when I'm plotting tangent, that's the first thing I'm putting on there is figuring out where my vertical asymptotes go. And so it's useful to know that for the tangent curve, they go at minus pi over 2 and the next one at pi over 2. So if I'm
Okay.
expanding that by a factor of 3, then I got to go from minus 3 pi over 2 to 3 pi over 2. And that distance between there is 3 pi, which is my period.
Okay.
So the only difference really between tangent and sine and cosine is sine and cosine have periods of 2 pi. Tangent's period is pi. And so the period for tangent is pi over b, not 2 pi over b.
Okay. Okay,
But
cool.
how you stretch it matters. In other words, whenever it's straddling the y-axis, you have to stretch it in both ways. You have to stretch it to the right and equally to the left. As opposed to cotangent. You got a cotangent one coming up?
Yeah, the next one.
What is it?
Y equals cotangent of parentheses theta plus 2 pi over 3.
Cotangents, asymptotes, are like this. Let me give myself some room. Let me make this pi out here. Because we're going to be phase shifting this thing. Cotangent is always decreasing. Like that. So this curve is y equal cotangent theta.
Yeah.
Now, the only difference is there's a phase shift. So is all I really do need to do on my phase shift is which way is it? The left?
Um, it is right?
It's left.
Left.
Remember that it's always x minus c, and if c is a positive number, I go to the right. If c is a negative number, I go to the left. Well, here, c is actually a negative 2 pi over 3, because this is the standard, x minus c.
Okay.
Just like everything else. Everything you had in math up to this point is always x minus h, x minus c, y minus k, You know what I'm talking about? With conic sections, with the vertex format of a parabola, all of them are minus. You don't run into a plus until you get to calculus. Finally, when you get to calculus, they have something that's f of x plus h. But every math prior to calculus, it's always a minus sign when you're subtracting something from x or y. Therefore, if it's plus, it's moving to the left because c is actually a minus 2 pi over 3. So all I'm going to do here is move my asymptotes 2 pi over 3 to the left. So if I call that minus 2 pi over 3, well, there's my first asymptote. And the period is still pi. So I've got to go to pi over 3. Right? The difference between minus 2 pi over 3 and pi over 3 is 3 pi over 3.
Okay.
Which is pi. So there's my new asymptote grid in red. Now I just draw the cotangent curve like I would normally draw it. Goes through the midpoint, down like that. And it doesn't go through the it doesn't go through the origin because those red lines are not equal distances from the origin. The original curve, that point right there is pi over 2. In other words, that is halfway between my two asymptotes. Well, this is halfway between my two asymptotes also. It's just that my two asymptotes are now at minus 2 pi over 3 and pi over 3. And then the next asymptote would come at 4 pi over 3.
Okay.
And one more period of the cotangent would look like that.
Okay, cool.
So I guess the moral is if you have vertical asymptotes, and everything does except sine and cosine. In other words, tangent does, cotangent does, secant does, and cosecant does. They all have vertical asymptotes.
Yeah.
When you're doing phase shifting, just move your asymptotes.
Okay.
That's probably the easiest way to do it. It certainly was on this one.
Okay, cool. Yeah. I understand that.
Because it's only a phase shift, which means it's only a horizontal shift. So I'm not changing the shape of the curve at all, because all I'm doing is moving it left or right.
Okay, cool. I understand
I can accomplish all of that by, in other words, I don't have to have a starting point and an ending point and a halfway point. I don't have to quarter it up when I'm doing cotangent and tangent.
Yeah.
But I do have to quarter it up when I'm doing the other 4.
Okay. Okay, cool.
Okay. What else we can do?
Well, the next one's find the exact value of each expression.
Okay.
So it is inverse cosine of -1/2.
We looking at an angle or a number?
A number.
An angle. Remember,
an angle.
We always take inverse trig functions of numbers to find an angle.
Okay.
We take trig functions of angles to get numbers. Remember how we were doing all of these problems when we had tangent of inverse cosine? Our very first step was to label that theta, right?
Yeah.
The reason I did that was because I wanted to make sure you knew you were looking at an angle there.
Okay.
Now, question is, what quadrant is that angle going to be in?
If cosine is negative, that can put us in the second or the fourth quadrant.
Second or third.
Oh, third, sorry. Second or third. And then
when you're dealing with inverse cosine, it prefers one over the other. Your calculator will never give you the third quadrant answer.
oh, it just puts you in the second.
Exactly.
Yeah.
So now we have to find the second quadrant angle where the cosine of that angle is equal to minus 1/2. Well, let's look at first quadrant angles. What angle is the cosine equal to 1/2?
At pi over 3.
Yeah. 60 degrees or pi over 3. Now to figure out, well, what's the equivalent second quadrant angle to 60 degrees?
2 pi over 3.
Right, or 120.
120.
In other words, 120, if I said, what's the cosine of 120? The answer would be minus 1/2.
Okay.
And that's also 2 pi over 3 if we're going to stick in radians. If I said, what's the inverse cosine of 2 pi over 3 and put that in your calculator, you're going to get an answer of minus 1/2. Or if you say, what's the inverse cosine of minus 1/2, is going to give you the second quadrant angle.
Yeah, okay.
If I was doing inverse sine of a negative number, it's going to be fourth quadrant. Sine goes in either first or fourth. Tangent goes in first or fourth. But cosine goes in first or second.
Okay. Okay. Cool. Another one is inverse sine of cosine pi over 6.
Okay, I'm going to work from the inside out. Now this is not one, I can't label that theta, because that's not an angle. That's a cosine of pi over 6 is a number.
Uh-huh.
What is it?
Cosine of pi over 6 is root 3 over 2.
So let's cross that out and put root 3 over 2 in there. And now what's the inverse sine of root 3 over 2? What angle and what quadrant are we going to be in?
We're going to be in the first quadrant.
Okay. Where is the sine equal to root 3 over 2?
Pi over 3.
Right.
Okay, cool.
So there's a fundamental difference between this problem and this problem. Notice the difference. In your problem, the inverse trig function's on the outside, the trig function's on the inside. In this problem, it's the reverse. And when it's the reverse, when the inverse is on the inside, this is where I label that theta and I draw my triangle.
Okay.
Because now I can dimension this triangle. If the inverse cosine is root 3 over 2, that has to be root 3, that has to be 2, that becomes 1. And now the sine of theta is 1/2.
Yeah.
Okay? So this translates into this method. Whereas never, you don't end up ever drawing a triangle to do the first your problem because we don't need to. In other words, we can actually figure out what the cosine of pi over 6 is, write that number in, square root of 3 over 2, and now we're just taking the inverse sine of square root of 3 over 2. So the fundamental difference is that when I've got sine of inverse cosine, I can solve it without figuring out the angle. I know that's an angle, but all I got to do is draw my triangle, label theta, and now this side is 3, that side is 7, this is square root of 40, and so the sine of theta is square root of 40 over 7.
Yeah.
And I didn't have to figure out theta. But when it's the other way around, in other words, when it's inverse sine of cosine, well, they're always going to give you a number here that you can figure out. In other words, if I did that one, I don't have to draw a triangle. It doesn't do me any good to draw a triangle. I have to figure out what that value is.
Yeah. Okay.
And that value is pi over 3. That's what the cosine of 1/2 is. So now I'm taking, no, excuse me, back up a second. That's always an angle. So that's pi over 3. And what's cosine of pi over 3? That's a number that I can figure out. That's 1/2. So I replace that with 1/2.
Okay, yeah.
I do have to figure out the inside when I do it this way. When I'm doing inverse trig of a trig function, I've got to work from the inside out and figure it out. I can't solve it without solving the inside. Unlike previous ones where we never had to solve for theta.
Yeah, yeah. Okay, well I have one more problem that's kind of tripping me up though on this. It's same as these.
What is it?
It's inverse tangent of cotangent 3 pi over 4.
So do the inside first. What's the cotangent of 3 pi over 4?
That's where I'm tripped up. I'm unsure.
Well, let's look at our 45-45 triangle. The dimensions are that.
Okay.
3 pi over 4 is the equivalent of 45 degrees, or 135 degrees. But its equivalent first quadrant angle is 45 degrees.
Oh, okay.
So cotangent of pi over 4 is 1. But 3 pi over 4 is in the second quadrant. So what's cotangent of 3 pi over 4?
-1, right?
-1. So I'm going to replace that with -1, and now the problem becomes the inverse tan of -1. Well, what quadrant is this? This is an angle. What quadrant is it going to be in?
That is going to be in the second quadrant?
Fourth. Remember, tangent and
the fourth.
First and fourth.
For
positive arguments, it's first. For negative arguments, it's fourth. For tangent and sine. Cosine, first and second. Okay?
Okay.
Now I'm looking for this angle where the tangent is equal to -1. And
that is
fourth quadrant.
7 pi over.
Well, the calculator will always give you a negative pi over 4.
Okay.
Notice that's the same as 7 pi over 4.
Yeah, it's just turning in a different.
It's not going to give you a 7 pi over 4 as an answer. It's always going to give you a negative first quadrant angle, which puts it in the fourth quadrant. In other words, angles, you just go clockwise instead of counterclockwise. So negative pi over 4 is indeed that 45-degree angle. That's theta right there. And that's negative pi over 4.
Okay.
Now whether you would lose, I doubt that you would lose points if you did coterminal. 7 pi over 4 is coterminal with minus pi over 4. So the tangent of 7 pi over 4 is also going to be -1. But let you know, when you're doing inverse sines and inverse tangents of negative arguments, it always gives you first quadrant angles with a negative sign in front.
Okay.
It doesn't give you this angle here. It gives you this angle here.
Okay. Cool. Cool.
All right, Nick, I got it 8 o'clock, so I will run and
Sounds good. Thank you very much, Mr. Cohen.
talk to you next time.